Chapter 13 is about personal financial management. That is a very, very important topic because when you think about it, you're spending a lot of time preparing yourself for a career or profession that help you make substantial amounts of money. Otherwise, you wouldn't be taking this class. And then you also spend considerable amount of time earning that money, actually doing what you're preparing to do. So you want to make the wisest possible investments with that money. And so that's why you really want to pay a lot of attention to chapter 13. And so first we're going to cover 13.1, the time value of money. And here we'll be examining the meaning of interest. Then we learn how to calculate simple interest, and then future value and present value, and then the miracle of interest, compound interest. And then we find the effective annual yield, and then how to use the rate of inflation to compare values over time, how they change, and you're all familiar with inflation. So let's get started. As we are examining the various sections, we'll be answering questions like, am I spending my income wisely? Or do I need a budget? Number 3, what are my financial priorities? Number 4, should I buy a home or is renting a better idea? Am I saving enough for retirement or for my children's college education? Am I taking advantage of available tax savings? Number 7, what are the best investment vehicles for me? So those are important questions, and as we go through the various sections, we'll be answering all these questions. First, let's talk about interest. And you're probably familiar with the idea that is, if we borrow an amount of money right now, today, we will repay a large amount later. This increase in value is known as interest. In other words, money gains value over time for the lender, that is. You have to pay more. On the other hand, if you save money and put it into an account that pays interest, then you get more later on because the bank had the use of your money. You can pay interest for that. And also, to some extent, it helps pay for the loss of the value of your money due to inflation. We'll talk about inflation later on. Now, the amount of a loan or a deposit is called the principal. So the interest is usually computed as a percent of the principal, and that is called the rate of interest, or the interest rate, or simply the rate. And then the rate of interest is always assumed to be an annual rate unless otherwise stated. And so there are two ways to calculate interest. One would be called simple interest, and then interest that's calculated on principal plus any previously earned interest is called compound interest. So simple interest and compound interest. So next, let's talk about simple interest. And so here's the formula for simple interest. If P is the principal, R is the annual interest rate, usually expressed in percent or as a decimal fraction, and T would be time and years, then simple interest I is calculated as follows. I equals P times R times T. Very simple formula, very powerful formula, and it's easy to remember too. So here's a little exercise. Find the simple interest paid to borrow $5,350 for 5 months at 4%. So in this case, P, the principal, equals 5,350. Our interest rate R is equal to 4%. And in decimal form, of course, it's 0.04. And the time is 5 months. So 5 months, that would be T, 5 months. But since the formula is given in terms of years, we're going to write this as 5 divided by 12 years, because there are 12 months to a year. So then our interest formula is equal to 5,350 for the principal. Then for the rate, times 0.04 times 5 divided by 12. And using a calculator, that's equal to $89.17. So that would be the amount of interest earned in a 5-month time period. So then the total amount we paid would be 5,350 plus $89.17 plus $89.17, and that's equal to 5,439 $5,439.17. So that's also called the future value. So the P, the principal, can also be thought as the present value, and the total amount would be the future value of the loan, because that is, in this example, 6 months in the future. So here then we have the formula for future value. If we have a principal P, it's borrowed at simple interest for T years at an annual interest rate of R, then the so-called future value of the loan, denoted by A, is calculated by this formula: A equals P, the principal or present value, times 1 plus R times T in parentheses. So that would be considered the future value of a loan. So here's an example of finding a future value for a simple interest. Searcher took out a simple interest loan for $210 to purchase textbooks and school supplies, and if the annual interest rate is 4.5%, and he must repay the loan after 6 months, find the future value, in other words, the majority value of the loan. So we apply, so here's our formula for the future value. A equals P times 1 plus R times T. And in this case, P is equal to $210 times 1 plus the interest rate being 4.5%, so it's 0.045. And 6 months means it's 6/12 of a year, 6/12 of a year, or 1/2 a year. And so we better use some brackets here. And so that is an equal to $214.73. $214.73. So that is the future value. In other words, that's what you will have to repay at the end of 6 months. Sometimes the future value is known, and we like to know what the present value is. So when we consider the formula for future value, A equals P times 1 plus RT, then we can solve this equation for P by dividing both sides by the expression in parentheses. 1 plus RT. So when we do that, then we have A divided by 1 plus RT equals P times 1 plus RT divided by 1 plus RT. And then, of course, we can cancel the 1 plus RTs. So then our present value would be A, future value, divided by 1 plus RT. So that's how we compute the present value when the future value is known. Let's apply this to the similar problem we just discussed a moment ago. And that says, suppose that Sergio, in the previous example, is granted a 6 months deferral of the $210 payment rather than a loan. That is, instead of incurring interest for 6 months, he will have to pay just $210 at the end of that period. If he has extra money right now, and if he can earn 1% simple interest on savings, what lump sum must he deposit now so that his value will be $210 after 6 months? Okay, so that's an application of the present value formula. And remember that P equals the future value, A, divided by 1 plus RT. So that would be $210 for the future value, $210 divided by 1 plus 0.01 times 6 months would be 6 divided by 12 of a year, a half a year obviously, and that is equivalent to $208.96. $208.96. What this means is that by depositing $208.96 now, that grows at a rate of 1% simple interest, then after 6 months there will be $210 in the account. Next, we'll be discussing compound interest. So interest paid on principal plus interest is called compound interest. And the way it works is that after a certain period, the interest earned so far is credited or added to the account, and the sum, the principal plus the interest, then earns interest during the next period. What this says is that you not only earn interest on the principal, but you also earn interest on the interest. And that's the magic behind compound interest. And so accounts can grow very rapidly. And in the book, there are comparisons between simple interest and compound interest. And that's on page 734 and 735. And so let's discuss the formula for compound interest. That's a very important one, that you'll be using quite a bit. And it's as follows. If P dollars are deposited at an annual interest rate of R, compounded n times per year, and the money is left on deposit for T number of years, then the future value A, the final amount on deposit, is calculated as follows. A equals P times 1 plus R divided by N, parentheses, to the N times T power. So it's an N times T, and that's the parentheses are raised to that power, N times T. So to find this future value, we need to know what P is, we need to know what R is, we need to know what N is, and we need to know what T is. And that's why you want to write these numbers down specifically when you're doing these kind of calculations. Here are two examples. Find the future value and the amount of interest earned for the following deposits for compound interest. A, for $3,419 at 2.1% compounded monthly for 30 months. So let's look at A. So here P equals 3,419. R equals 0.021. And N, compounded monthly, means 12 times a year. And for 30 months, so 30 divided by 12, that would be the number of years. Or 2.5 years for T. So then our formula would look like this. A equals P, 3,419, times 1 plus 0.021 divided by n, which was 12, or which is 12, to the n times t, and n is 12, and t is equal to 2.5 years. So this will help. So when you have a scientific calculator, and when you have a smartphone, many of the smartphones, when you hold the calculator in landscape mode, you can raise numbers to a power, and so here the power would be 30. This expression to the 30th power, and the way you evaluate this this expression is you go by order of operations. Remember, order of operations was PEMDAS, PEMDAS. You may remember that. That's the order of operations. And the P stands for parentheses first, and then exponents, and then multiplication, and then division, then addition and subtraction. So here we evaluate the expression in parentheses first, and so you divide 0.021 by 12, you add 1 to it, and then you raise that to the 12 times 2.5, which would be to the 30th power, and then you multiply it by 3,419, and that would give you a value of $3,603.13. So that would be the future value. And the interest earned, that was the second question, the interest earned is equal to the future value minus the present value. In other words, it's 3,603.13 minus 3,419. So the interest earned is then equal to, let me move it up so you can see, is then equal to $184.13. So that's the amount of interest. For part B, we asked the same thing, find the future value and the amount of interest earned for the following deposits for compound interest. So here the principal is 12,450. R is equal to 3%. It's compounded quarterly, that means n equals 4, and t equals 5. So P equals 12,450. R is equal to 3%, or 0.03. quarterly compounding means n equals 4 and t equals 5. So then applying the formula, the future value, A equals P times P because 12,450 times 1 plus 0.03 divided by 4 to the n times t, 4 times 5, which would be the 20th power, obviously. 4 times 5 is 20. Again, we evaluate this expression from the inside out. We divide 0.03 by 4, add 1 to it, raise it to the 20th power, and then multiply that result by 12,450, and that becomes then 14,456.74. And again, the interest earned is the future value, which we just computed, minus the present value. So that's 14,456.74 minus the present value of 12,450. So the interest earned in this case is 2006.74. 2006.74. So there you have two simple calculations for computing compound interest. So again, let me just write the amount of interest earned, $2,006.74. Future value minus present value. Sometimes we need to find the present value for compound interest. And so when we look at the formula for future value, A equals P times 1 plus R divided by N to the N times T power, we can solve this formula easily for P by dividing both sides by the expression in parentheses. So that, in other words, P is equal to A divided by 1 plus R divided by N to the NT power. Okay, so here's an example where we can apply this formula. Ashley will need $40,000 in 5 years to help pay for a college education. What lump sum deposited today at 3% compounded quarterly will produce the necessary amount? Okay, so that's an example where we want to find out what the what needs to be deposited. Let me just move this down so you can read the problem statement. So, so we know that the future value in this case is 40,000. So let's write down the numbers. A is 40,000. That's what is needed in the future. And we know that T is equal to 5 years. And the interest rate is 3% or 0.3. And compounded quarterly means n equals 4. So using these amounts, then P, the present value that we want to calculate, P is equal to 40,000, the future value, divided by 1 plus 0.03 divided by n, which is 4, to the n times t power, which means 4 is n, and t was equal to 5 equal to 5 years. And when you do this correctly again, so you evaluate the expression in parentheses, you raise it to the 20th power because 4 times 5 is 20, and last you divide that into 40,000, that would be equal to $34,447.59 that you would invest right now. So, and then in 5 years at 3% compounded quarterly, she would have her 40,000 that she would need at that time. So that's what needs to be deposited today. So you can even try this for yourself. You say, okay, I want to have a certain amount of money in so many years and have this interest rate to work with, and so many years. So how much would I have to deposit today as a lump sum to have that much money in the number of years that you want to have it? So it's a great little example and can have a lot of applications. Let's use the future value formula for compound interest to find the time required to double a principal deposit. Okay? So in other words, the formula for future value, of course, is A equals P times 1 plus R divided by N to the N times T power. And now we want the future value to double the principal. In other words, we want 2P equal to P times 1 plus R divided by N to the N times T power. Well, you look at this equation here, and you notice we can divide both sides by P. So then 2 equals 1 plus R divided by N to the N times T power. And so if an investment account is paying 3% interest, here's a specific example, and is compounded daily, then when will the amount in the account be twice the original value? So in other words, now we have R equal to 0.03 and N equals to 365. And so now we want to know what is T. What is T equal to? So that's the question. So we use the information we have in this expression here. So 2 is equal to 1 plus 0.03 divided by 365 to the 365 times T power, N times T, 365 times T power. And so we want to know what T is. So we're going to make use of logarithms, and that says that if A equals B to the N, then the log of A equals the log of B to the N, and that's equal to N times the log of B. Then we divide both sides by log of B, so N equals the log of A divided by the log of B. In the same way, we apply that formula here. So then the log of 2, taking the log on both sides of this expression, so log of 2 equals the log of 1 plus 0.03 divided by 365 to the 365 times T. And that then is equal to the log of 2 equals, and now we multiply the this expression by 365 times t. 365t times the log of 1 plus 0.03 divided by 365. And then, in other words, t then, well, let's divide by this expression first. So let me switch sides. So 365 t equals the log of 2 divided by the log of 1 plus 0.03 divided by 365. And then finally we divide both sides by 365 to isolate t in this expression. So we divide by 365 on both sides. So in other words, we have t equal to the log of 2 divided by 365 times the log of 1 plus 0.03 divided by 365. And that turns out to be 23.106. And remember, this is now years. And that's not a very helpful expression, except for the 23 years. So what is 0.106 of a year? Well, that's about 23 years and about 39 days. So it is, again, this is mathematically correct, but it's not a helpful expression. So we need to convert the 106 to 39 days. And so that will be the answer. So in other words, that investment would double, given that the interest rate is 3% and it's compounded 4 times a year. It would take 23 years and 39 days to double. Next, we're going to compare retirement plans. So here are the results. What happens when you start saving for retirement. And in Plan A, a person, Annika, begins saving at age 20 and deposits $2,000 on every birthday from age 21 to age 35. In other words, 15 deposits of $2,000 each, or $30,000 total, and after that makes no further contributions. Plan B, here somebody, Barry waits until age 30 to start saving, and then makes deposits of $22,000 every birthday, just like Annika did, from age 31 to age 67. In other words, 37 deposits of $2,000 each, or a total of $74,000. And look what happens when these retirement plans, grow at how soon or how much they grow. So keep in mind that both plans pay the same amount of interest, 6% per year. And so how this begins to build up. So Annika saves money, and so at age 20 she has nothing, and neither does Barry. But at age 25 she has 11,274, etc. So every 5 years we can see how her account has grown. And so now again, at age 35, she no longer pays into the account. From now on, it's all interest and compound interest. So you can see how this account grows. And at age 67, if we scroll down here, she has little over $300,000 in her account. Again, that's for a total deposit of $30,000. On the other hand, Barry does not start early, but he waits, and at age 30, he begins to put money in there, and you can see the amounts grow, 11,274, etc. It's the same one, but at age 67, he only has $254,536 in his account. So 55,000, well, almost $55,000 less. What's the difference? Well, this is basically a demonstration that it pays to start early with putting money aside. And it is always a challenge for most people to put money aside because everyone needs money now, and that's understandable. And so you have to figure out a way how to do that. We have found a good way to do that, and others have also. It's not a secret. And that is if you can make payroll deductions into some account that you don't touch and let it grow like Anika did. What's a little bit more difficult today, of course, is that 6% interest rates are very difficult to get, if at all. And so be careful where you put in your money with 6% interest. But there are certainly investments possible that pay more than this, very small amounts that you get from money market accounts. So you need to shop around and see what is available. And so maybe you want to find a financial advisor who can help you invest your money wisely and safely. So, but this is a great example that it pays to start saving early. Let's talk about the effective annual yield. You may have seen this in banks and other financial institutions. And so they have the nominal or the stated rate of interest and the second rate that would produce the same final amount or future value at the end of 1 year if interest were being paid per simple rather than compound. And that's called the effective rate or the effective annual yield or simply the yield, abbreviated sometimes APY or simply with the letter Y. And because the interest is normally compounded multiple times per year, the effective annual yield will usually become somewhat higher than the nominal rate. And so here's the formula. The effective annual yield, Y equals 1 plus R divided by N to the nth power minus 1. So be sure to, when you compute the yield, that you subtract 1 from this expression. Okay, so when is this a good idea, or when can you even use this? Well, let's suppose you want to compare savings rates at a bank. So there are three ways to invest money. So here's how you can use the yield formula. And so Yolanda wants to deposit $2,800 into a savings account and has narrowed her choices to 3 institutions represented here. Which is the best choice? Friendly Credit Union offers 2.08% annual rate, compound monthly, and then the Premier Savings has a 2.09% annual yield. So we already have that one, what the annual yield is. And then the Neighborhood Bank offers 2.05% compounded daily. So when we compute the Friendly Credit Union yield, we get the following. So for Friendly, the yield would be 1 plus 0.0208 divided by 12 to the 12th power minus 1, and that is equal to 0.0210 or 2.1%. And then for the Premier Savings, we already know what the annual yield is. They gave it to us, Friendly, the Premier rather. y is equal to 2.09%, as given in the problem statement. And then for the neighborhood bank, neighborhood, y is equal to 1 plus 0.205 divided by 365, because that's compounded daily. So divide by 365 to the 365th power minus 1. And that would be equal to 0.0207 or 2.07%. And when you compare these three rates, 2.10%, 2.09%, 2.07%, of course, friendly wins with 2.10%, and that's where she's going to put her money.